In this video, we're going to take a look at reflections and rotations. So let's start off with reflections here, where you should be familiar with the fact that any linear transformation can be defined by the effect it has on the unit vectors 1, 0 and 0, 1. So we have 1, 0 and we have 0, 1. Okay. Now, if we have a transformation that's represented by the following matrix here, so we have the matrix M, which is equal to A, B, C, D. Okay. Then this transformation will map 1, 0 to AC. So 1, 0 maps to AC. And 0, 1 will map to BD. Okay. So 0, 1 maps to BD there. Now this is really important because this property here allows us to easily derive the reflection and rotation matrices. Now for reflections and the reflection matrices, there's 4 key reflections for A-Level Further Maths that you need to be familiar with. So we have reflections in the coordinate axes, so a reflection in the x-axis and a reflection in the y-axis. And we also have reflections in the line y equals x and y equals minus x. Okay. So to begin with here, let's take a look then at reflection in the x-axis. So for a reflection in the x-axis here, let's do this at the top. So for reflection in the x-axis, what I'm considering here then is what happens to these points, so 1, 0 and 0, 1, under a reflection in the x-axis. So if it helps, do a quick sketch here just to see what's actually happening. I'll do it underneath here. That's my y-axis. And this is my x-axis here. So these 2 points, 1, 0 and 0, 1. So I've got 1, 0 here. 1, 0 and 0, 1. Okay. So under a reflection in the x-axis, what I can see then is 1, 0 would map to itself. So that won't move. Okay, so 1, 0 will map to itself. And then this point here, 0, 1, that would map to 0, minus 1. Okay, so underneath the x-axis there. So 0, 1, that will map to 0, minus 1. Like so. So using these mappings now, we can easily derive the 2 by 2 matrix that represents a reflection in the x-axis. So the 2 by 2 matrix here that represents a reflection in the x-axis is given as, so we use 1, 0 as the first column, so 1, 0, and then 0, minus 1 is my second column, so 0, minus 1 there. Okay, so I can see then that the 2 by 2 matrix here that represents a reflection in the x-axis is given as 1, 0, 0, minus 1. Okay, now just one other important point here to make. So this point here, 1, 0, is what we actually call an invariant point. So points that do not move under the given transformations are what we call invariant points, and lines which do not move are called invariant lines. So in this case here, the actual x-axis is an invariant line. Okay, so the equation y equals 0 is the equation of the invariant line there. So for a reflection in the x-axis, we say then that y equals 0 is an invariant line. Okay, so y equals 0 is invariant. Okay, so that's a reflection in the x-axis. I'm going to quickly clear the screen here now so we can have a go at a reflection in the y-axis. So now for a reflection in the y-axis, again, I think a sketch is really helpful here to identify what's actually happening. So again, if I do it underneath here, don't need to be perfect, but that's my y-axis there. That's my y-axis. We have our x-axis here, and we have the 2 points of 1, 0 and 0, 1. Okay. So now if we reflect in the y-axis here, what would actually happen? Well, I can see that 1, 0 would map to minus 1, 0. That maps to minus 1, 0 there. And then 0, 1 would map to itself. Okay, so let's do it underneath. 1, 0. This maps to minus 1, 0. Like so. And then 0, 1 maps to itself. So 0, 1 maps to 0, 1. And again, we can easily use these mappings now to identify our 2 by 2 matrix that represents a reflection in the y-axis. So the 2 by 2 matrix here that represents this is given as minus 1, 0, and then 0, 1. Okay. So this 2 by 2 matrix here represents a reflection in the y-axis. And again, in terms of invariant lines and invariant points here, x equals 0 would be the invariant line in this case. So in other words, the y-axis itself. So x equals 0 is invariant. So that covers a reflection in the y-axis. So now moving on to a reflection in the line y equals x here. So again, I'm going to draw a quick sketch just to help illustrate this point. So that's my y-axis here. And then we have our x-axis here. Now, because we're reflecting the line y equals x, I need to sketch that line. So if I do that in red, not going to be perfect, I'm doing it freehand, but it'll look, say, something like that. Okay, so that's the line y equals x. And again, working with these 2 points then of 1, 0 and 0, 1. So with a reflection in the line y equals x, what I can see is the point 1, 0 will map to 0, 1 because we're reflecting the line y equals x. So 1, 0, like we said, that maps then to 0, 1. And then 0, 1 will actually reflect the other way. So 0, 1 will then map to 1, 0. So 0, 1 will map to 1, 0. Okay. And again, using these mappings here to identify our 2 by 2 matrix that represents a reflection in the line y equals x, we get, I get 0, 1 and 1, 0 there. Okay. So that covers a reflection in the line y equals x. And finally then, let's take a look now at a reflection in the line y equals minus x. So for a reflection in the line y equals minus x, again, we're going to use these axes here and the 2 points that we're working with here of 1, 0 and 0, 1. Okay, so we've got 0, 1 here and 1, 0. So now what we're going to do here is reflect these in the line y equals minus x and see where these map to. Okay, so what about 1, 0 here? Well, that would map to this point here, which is 0, minus 1. In that case then, 1, 0, that maps to 0, minus 1. So 0, minus 1 there. And then what about 0, 1 here? Well, that would map to this point here, which is minus 1, 0. Okay, so 0, 1. So 0, 1. That maps to minus 1, 0. Okay, like so. And then from here, from our mappings, we can now easily identify the 2 by 2 matrix that represents this reflection. So in this case here, the 2 by 2 matrix that represents this reflection, that would be given as 0, minus 1, and minus 1, 0. Like so there. Okay, so this 2 by 2 matrix here, that represents a reflection in the line y equals minus x there. Now, I forgot to mention it for a reflection in the line y equals x, but we do also have invariant lines for these two reflections. So for reflection of the line y equals minus x, in this case, the actual red dotted line itself, so y equals minus x, is the invariant line here. So y equals minus x is invariant. And then for a reflection in the line y equals x, so reflection in y equals x, the invariant line here would be y equals x itself. So y equals x is invariant. Okay. And there we have it. So that's everything that we need there for reflections now. So let's take a look at rotations. So let's take a quick look at rotations. Now, before we take a look at any actual rotations here, it is important to mention that for A-Level Further Maths, we always work anti-clockwise about the origin. Okay, so we start off with these 2 points again, so 1, 0 and 0, 1, and we consider then how a rotation maps those points. Okay, so let's start off then with a rotation of 90 degrees anti-clockwise about the origin. So a rotation here of 90 degrees anti-clockwise, which I'll just shorten to AC, about the origin, so about 0, 0. Okay, so what I need to do here is quickly sketch my axes. If I do that in the top right corner here, I've got my y-axis and I've got my x-axis here. And we've got these 2 points again. So like we said, we've got 1, 0, and we have 0, 1. Okay. And all I'm going to do here now is just consider what happens to these 2 points and where they map to after this rotation here. So if I go 90 degrees anti-clockwise, let me do this in a different color. Let's do this in red. Then this point here, 1, 0, we're 90 degrees anti-clockwise. That will map to 0, 1. Okay, so 1, 0 maps to 0, 1. Like so. And then this point here, 0, 1, that will map to here, which is minus 1, 0. So 0, 1. This maps to minus 1, 0. Okay, so this point here is minus 1, 0. Like so. So from here then, we can now easily see the 2 by 2 matrix that represents a rotation of 90 degrees anti-clockwise about the origin. So this matrix here is given as 0, 1, then minus 1, 0. So 0, 1 for the first column, and then minus 1, 0 for the second column. Okay, so that's our first rotation there. So now if I go back to my original pen color here, what about a rotation here then of 180 degrees anti-clockwise about the origin? So a rotation of 180 degrees anti-clockwise about the origin. What would that be? So again, let me do this in a different color. I'll do this now in green. So again, we start with these 2 points here. So now if I go 180 degrees anti-clockwise, starting with 1, 0, we're going to go from here all the way around, will take us to this point here. So now I can see that 1, 0 maps to minus 1, 0. So that maps to minus 1, 0. And then we have 0, 1. So 0, 1 going 180 degrees anti-clockwise, keep going round. And that will take me to this point here. And this point here is 0, minus 1. Okay. In that case, then 0, 1 maps to 0, minus 1. Okay. And again, we can easily identify the 2 by 2 matrix here then that represents this rotation. So our matrix here will be minus 1, 0, minus 1, 0, and then 0, minus 1. Okay. And then all that's left here then is a rotation. Go back to my original pen color. A rotation of 270 degrees anti-clockwise about the origin. We've got rotation of 270 degrees anti-clockwise about the origin. Okay. So again, just representing this rotation here, I'll do this in blue now. Again, we start with these 2 points. I've got 1, 0 here. So if I now go 270 degrees, so this would be 90, this would be 180, so this would be 270 here. So I'm going all the way around, and that takes me to 0, minus 1. So here then I can see that 1, 0 maps to 0, minus 1. Okay, so 1, 0 maps to 0, minus 1. And then we have 0, 1. So now we're not 270 degrees here anti-clockwise. This would be 90, this would be 180, and this would be 270. So I can see them. That 0, 1 will map to 1, 0. Okay. That will map to 1, 0. Okay. So again, we can now easily identify the 2 by 2 matrix here. So I'm going to get 0, minus 1 for my first column, 0, minus 1, and then 1, 0 for the second column. Like so. Okay. And there we have it. So those are the 3 key rotation matrices that you need to be familiar with. I wouldn't say it's worth memorizing these 3 matrices here. What I would say is just, be sure that you know how to derive these results using this method here. You can easily derive them, like you can see, just with a bit of basic work. So nothing too challenging there. Now, the final thing to point out here is, what about when we're working with, say, a rotation that isn't a multiple of 90 degrees? So what about if we was rotating, say, 45 degrees anti-clockwise? How would we do that? Well, what we do is we use our general rotation matrix. So for the general rotation matrix here, this is a 2 by 2 matrix, and this is given in the formula books. You don't need to even worry about memorizing this 2 by 2 matrix. So for the general rotation matrix, like we said, it's a 2 by 2 matrix. So my first element here in the top left corner is cosine theta. For the top right element, this is minus sine theta. So minus sine theta. In the bottom left element here, we have sine theta. And then finally, for the bottom right element here, again, we have cosine theta. Okay. So this is what we call the general rotation matrix. And this takes an angle theta anti-clockwise about the origin. Okay, so this gives us a rotation through the angle theta anti-clockwise about the origin. So there you can see, this is really useful if we're working with angles that aren't a multiple of 90 degrees. So for example, if we were rotating 45 degrees anti-clockwise, or say 30 degrees anti-clockwise, or say 135 degrees anti-clockwise. In that case, we want to use this general rotation matrix. So the only thing left to mention here then is invariant points for rotations, and we only have one invariant point for any rotation, and that is the origin 0, 0. So if I quickly make a note of that here, the only invariant point, so the only invariant point here for rotation is 0, 0. So in other words, the origin there. Okay. And there we have it. So that's everything that we need there for rotations. And that brings us to the end of this video on reflections and rotations.